So back to the continuity equation, I wanted to show you the more rigorous mathematical way. And again, I will use the new Pelikan M120 green-black special edition, which replicates the vintage one from the 1955. And I've used as I did before, I have used this Pelikan 4001 dark green ink. So we saw before that the simplified version of the continuity equation is for a fluid tube that changes diameter, let's say. So the fluid moving from point 1 to point 2, where the cross-sectional area changes, in this case decreases, from A1 goes to A2, and the speed must change, so that for a steady state flow, the same mass per unit time goes through this cross-sectional area in both points, so there is no mass accumulated in any one point or lost, and the density remains the same, and also it's not a function of time. So incompressible fluid, steady state flow, density being everywhere the same implies that the product of the area times the speed is constant. And this is what in the IB, in option B, the engineering option, in the fluid mechanics part, this is what can be used, and this is the continuity equation. And it is often combined with a Bernoulli's equation to solve all kinds of problems. Okay, now the most complete form of this equation is the following. Consider that now instead of net flow of mass being 0, there is a net flow of mass. So I will make this in this kind of coordinates, where this is the x direction, this is y and z. So imagine that this is the volume now, this is the flow tube. And that the fluid flows in this direction. So now there is this dm dt, the rate of mass flow at this point, and then there is dm dt at point, let's say, x plus delta x. This is at point x, where x could be 0. It doesn't matter. So in a steady state flow, we said that this is the same. There is no change in the mass flow, in the rate of mass flow between 2 points. But what if there is a special variation of this rate? In other words, let's make, and this is what I mean by delta x, the difference between these 2 points. So if we remember what the definition of a partial derivative is, or a derivative, this is the change between these two over the distance delta x, and take the limit as this delta x goes to 0. So dm dt at, let's say, x plus delta x minus dm dt at x over delta x, and take the limit as delta x goes to 0. And this is actually the partial derivative of this flow rate with respect to x. Now, dm dt we did this before. We said that M is the density times the volume. Remember, the density was mass over volume. So mass is the density times volume. And we said that this was in a sense rho, the volume was the area times x, and then the area and the density being the same, being constant, dx dt was the speed. So this has units of mass per unit time. And I will use this here so that, and this is in one direction, in the x direction. The special variation, or the x derivative of this is and this is what I mean. Let me take the area out because it's constant, and then I have the special derivative, or the x derivative or the space derivative of the product rho times v. So if there is a change in the flow rate of the mass between these 2 points, this is expressed as the special derivative of this. So this means that, what is this thing here? This is the flow rate per unit cross-sectional area. So if I divide by A, then this must be equal to, let's see, what are the units of this? This is density per unit length, and speed is length per unit time. So this thing has units of density per unit time. So this gives how fast, or the rate that the density inside this volume changes because of difference in mass flow or density flow at the 2 points, at the 2 cross-sectional areas. And I have to use a minus here, because if this is positive, that means that more mass is flowing out of this cross-sectional area than the incoming cross-sectional area, then that means that the density inside decreases. So I have to use a minus here. And then the final step is to transform this into 3 dimensions. What this is in 3 dimensions is basically the divergence of the product rho times v. So this in 3D, this becomes the divergence of rho v, where for v now I use the vector, and then I will bring this to the other side, plus the temporal variation of the density inside the volume is 0. And this is the complete form of the continuity equation. And again, this means that there are no sinks or sources inside this volume. In other words, no cause of creating mass or losing mass, or mass disappearing inside this volume. The density changes only because there is a difference in the flow rate between these the two cross-sectional areas. Cases where this may not be 0 would be, for example, in the plasma. If we consider the continuity equation for one species of the plasma, let's say electrons or ions, and for some reason you generate ions, you have ionization, for example in the ionosphere, or neutralization of ions and electrons. So some species disappears. So in that case, this may not be zero, and you have to consider sinks and losses. But in most cases where you have like a neutral fluid, in fluid mechanics, this is the continuity equation. Okay, thanks for watching.